Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Pacific Atlantic water flow. And as you can see that this problem hasn't been asked in too many companies. The thing is, the companies where this problem has been asked are really one of the most important companies in the world. Google, Amazon, Uber, Microsoft, Facebook, Apple, ByteDance, which is a parent company of TikTok, Bloomberg. So you can understand the scale that why this problem is important and what kind of companies ask this problem. And the thing is, main intention for understanding this problem is to not to understand the actual problem, but rather the approach behind the solution, because that can become a base foundation for too many other problems. There is a lot of information in this problem statement, but if we try to comprehend this using the picture, it's really simple to understand. So I'm just going to go over that. Essentially, we are given a grid like this, and we are told that this is actually an island or somewhere in the ocean. But the thing is, it is at the cross junction between Pacific Ocean and Atlantic Ocean. And the way it represents is that this top and this left edges, they are actually Pacific Oceans, and this bottom and this right edges, they are Atlantic Ocean. So this, and the second information we are given is that all of these coordinates inside the given island represents the height of that particular area. And why the height is important? Because we are told that on this particular island, on this particular grid, there happens to be a lot of rain, which means that rain falls, and we know the property of water that it gets transferred from higher height to lower height. We are also told that that rain at any particular cell can can go to four directions. It can go to top, right, bottom, or left, which means it cannot go diagonal in any scenario. And the condition that if it can traverse from one cell to another cell is that if the height at any particular given cell, if it's greater than or equal to the cell we are trying to reach, then the water can travel to that cell. Which means, suppose we take this cell for an example, the height for this cell is 4, which means if the rain falls on this cell, we can conclude that the rainwater will go to cell 3. It will also go to cell 1 and cell 2, but it would not go to this cell 5 because the height at cell 5 is greater than cell 4, which means that this is cell 4 and this is cell 5, so water can't travel like this. Now the interesting part for this question is that we need to understand that what are the cells in the given grid that can travel where if the rainwater falls, it can travel to both Atlantic Ocean and also Pacific Ocean. So let me clean this up a bit. Suppose we consider this cell number 5, and if rainwater falls in the cell number 5, let's see that can it reach Atlantic and Pacific. Like, we know it can reach, but in this cell adjacent to the cell number 5, the height is 3, which means water can go over here. From this 3, the water can go to this 1, and because this is at the edge of Atlantic, of course water can go to Atlantic Ocean from here. Now from this cell number 5, we know that water can also go on this side because the height is 4, and from this 4 the water can go because the height is 2, which is less than 4. And from this is at the edge, which means that at any point whatever the height over here is, like 1, 2, whatever value, all of that can go to Pacific Ocean. So we can conclude that water from this cell number 5 can reach to both Atlantic and Pacific Ocean. Let's take another example. Suppose we take an example of this value number 4. So we know that from this cell we cannot go over here, we cannot go to 5, but we can go to 2, and from 2 we can go to Atlantic. So that concludes one option. Now let's try to see that can we go to Pacific Ocean. So first, if we try to go on top, okay, we can go over here because this is 3, but from 3 we cannot go to the top because this is 4, so we can't go Pacific in this direction. If we try to go over here, we can reach to this 1, we cannot go to this 7, which means that from this 4 we can go to Atlantic Ocean, but we cannot go to Pacific Ocean, so we wouldn't include this in our intersections. For every single cell, we are going to check that whether it can reach to both Pacific and Atlantic Ocean. If it can reach, we will just maintain a list or some sort that will take care of all the cells that we are able to reach to both the oceans, and we would keep on adding them in this list. So first we'll start with this first element. We know that it can reach to Pacific Ocean, but it won't be able to reach Atlantic Ocean because height over on both these cases are greater. So we wouldn't include this. We would go to next one. So over this, this again can reach to Pacific, but it cannot reach to Atlantic because it will traverse in these two directions, but it won't be able to go any further over here and over here. Same happens for this one, and basically this solution would work. We would find our answer. Eventually our list would be filled out. Suppose we are at this location 5. So we know that this is at the exact intersection of both the oceans, and it can clearly go to the rainwater can clearly go to Pacific and both Atlantic. So we would add this particular location in our list, and eventually the list will be filled out. But the thing is, the issue with this approach is that in terms of time complexity, we are actually doing a lot of repetitive work, because for every single cell we are checking all the possibilities, and we might end up doing, in the worst case scenario, big O of. So suppose this is M and these are N cells, so we can say that the time complexity would be big O of M multiplied by N squared, because for every single cell we will have to iterate over all the other cells, and this is not a very good time complexity. There exists a better approach. So in order to solve this problem, we are actually going to use a different approach, and the approach we are using is actually, if mountain cannot come to Muhammad, Muhammad will have to come to mountain. And what I'm trying to say is, suppose that rather than checking at any particular cell that whether it can reach both Atlantic and Pacific Ocean, we create two separate grids. So suppose we create a grid and another grid, so two separate matrix of Boolean values that has the same size of whatever the input size we are given. And at any particular location, we just name that okay, this matrix consists the data of all the cells that can actually reach the Pacific Ocean, and this matrix contains all the data of all the cells that can actually reach to the Atlantic Ocean. And once we have these two matrices defined, the moment we find that okay, so over here we know that this particular element 3, this can reach to Pacific Ocean. So over here, suppose this value corresponds to this 3, so we will set the value as true over here. And same goes on this side, that suppose we find out that this particular element at position 4 can reach to Atlantic Ocean via this way. So whatever the corresponding value we have over here, we will set that value as true, and eventually we will have the entire matrices filled out. And once we have those, all we need to do is just intersect both of them and find the common elements between both of these matrix, and that would be our final list of matrix that contains all the cells that can reach to both Pacific and Atlantic Ocean, and this would be our solution. Well, this solution actually works pretty fine, it's pretty efficient, and all we need to do is we need to figure out that how we are going to generate these two matrix and what are all the different logic we are going to take. Let's take the most basic approach. I'll be showing you an example that suppose we want to reach to Pacific Ocean, how can we fill out that matrix. Now, what is the most basic thing we know about Pacific Ocean? Well, we know that for this particular island, all the cells that are present in this row and all the cells that are present in this column, they are actually at the edge of the island. Also, they are at the very adjacent to Pacific Ocean, which means all the water in these positions can actually reach to Pacific Ocean in all the cases. So in our matrix, whatever matrix we have, we can basically define all the elements these positions as true, because we know that they can reach to Pacific Ocean. Now, previously at any particular location, we were actually trying to go outwards to see if water can reach to adjacent cell or not. But rather than going outwards, why don't we come inwards from the cells we already know that can reach to Pacific Ocean? So over here, these cells we already know that they can reach to Pacific Ocean. So if we check that whatever the cells that are adjacent to these cells from this particular cell that can reach to Pacific Ocean, can we reach to these adjacent cells or not? And the moment we find that okay, we can reach to some adjacent cells that we haven't already visited, so we can set that as true. Suppose the value over here is 3 and we know that this is able to reach to Pacific Ocean, and suppose the value adjacent to this one is actually 6. So we know that since the height difference, there is a height difference, and over here we need to check the reverse height difference. Previously in this approach we were actually checking that whether the height we are currently at and the height the adjacent cell is actually the height is lesser than whatever the current height we have. Over here we are coming inwards, so we will check that whatever the next cell is that we haven't checked, whether its height is greater than whatever the height we currently are at. So in this case this is 3, this is 6, which means that okay, from this cell we can come to this cell, and over here we know that we are coming to this cell from this particular cell that is already able to reach to Pacific Ocean. So over here we can directly mark this one as true, and we won't have to do lot of calculation over here because we already know that this cell is true and we are reaching to this cell via this cell, and this would be a very good solution. And this is how we can actually fill out this entire matrix or like all the remaining portion in big O of m cross n times in just single traversal, because we are not, for any particular cell we are not going to check the whole thing, we are only going to check the cell that is exactly adjacent to it. Suppose we are at this particular cell and we know that this cell can reach to Pacific Ocean, we have already set this value as true. Okay, now we do calculations like this, and suppose before we come over here from this route we have already calculated this and we know that this is already true, that this can already reach Pacific Ocean, and we are at this position and we are checking this again. So first we will already find that whether the value for this particular element has been calculated already or not. If it has been calculated, we don't need to do repetitive work and we can just simply skip over it. That way we can also make some runtime adjustments that would be more efficient on our case. Okay, now we need to find a way to somehow create the matrix that stores the information of all the cells that can reach to Pacific Ocean and also to Atlantic Ocean. In order to do that, at first I thought that we are going to use dynamic programming over here, and the reason I thought is because first of all we are defining a set of all the cases that can reach to Pacific Ocean, so this becomes our base case. Once we have our base case defined, we are essentially going in all the directions to see that if we can reach to next cells, and suppose in this case we are able to reach to this cell from over here due to the height difference, so we will mark this as true, and again from over here we will again do the same thing, and we will, so basically at any point we are using whatever the calculation we have calculated before to generate the next results. So that's a very clear indication that we need to use dynamic programming over here. But it turns out that I was not able to solve it efficiently. I was still missing out in a lot of test cases. So apparently dynamic programming is not the way to go, but I still urge that if anyone can solve it using dynamic programming, I would be more than happy to understand your approach. So second thing I tried to do is okay, in order to solve this we need to iterate over the entire matrix, and in order to iterate over the entire 2D matrix we have basically two methods. We can use either breadth first search or we can use depth first search to iterate over all of the elements and do some calculation. Now I'm new to graph theory and I need to first of all perfect myself on depth first search before I move towards solving the problems using breadth first search. So I chose the approach of taking depth first search, but it can also be solved using breadth first search without any issues. And we know that in order for us to complete this program using depth first search, we need to use recursion over here, and of course we can use recursion because notice that at every single position, so over here first of all we define that this can reach to Pacific Ocean. Now we move on all the directions and over here we find the height difference. So again we know that this can reach to Pacific Ocean because this can reach to this cell, so we mark this as true, and then again we repeat the same process that we have just did, and again we would mark this as true, and again we would repeat the same process. So essentially we are doing the same sort of work but for different inputs, and that's a very clear indication that we need to use depth first search using recursion. And let's move on towards coding now. First of all, we are going to check the condition that if the given input is actually an empty matrix, then we just need to return null. Okay, if that's not the case, let's create two parameters to store the value of row and column. Now we'll create two Boolean matrix to see if to store the value of cells that can reach to Pacific and Atlantic Ocean, and we are going to name that Pacific reachable and Atlantic reachable. And we are going to create both of them to the size of whatever the initial heights matrix we are given. Now we will run a for loop on the for both the matrix to be filled out. In order to fill both the matrix, we are going to create a DFS method, and inside the DFS method we are going to provide the row and column location, and we are also going to provide a Pacific and Atlantic matrix. So first we'll do it for Pacific matrix, and we are also going to provide the input heights that we are given. We are again going to call the same function for the Atlantic. We'll iterate using column as well. Now before we calculate the result, first let's create the method. Now inside the DFS method, we will have to iterate over for any particular cell. We will have to iterate over all four of its adjacent cells. So we'll just create a 2D array called directions, and we are going to use it to iterate over all the adjacent or neighboring cells. So we are at this DFS location, which means that we already know that this row and this column pair is already able to reach to subsequent whatever reachable matrix that we are trying to calculate. So which means that we will set that value as true. Now we will start iterating over the neighbors of whatever the current cell we are at, and we are going to create the new row and new column. Now we will have to check that if this new row and new column, are they out of bounds or not. If that's the case, we just ignore that and we continue. We also check that if we have if the new row and column cell if we have that value calculated before, we can also just ignore that case. Okay, if both the cases are not true, we will check that if the height difference of the previous cell and new cell is in our favor or not, which means if the heights for the new row and new column if that is greater than or equal to whatever the previous height was. If that is true, we will need to call the DFS function again with the new row and new column. And this would be our logic for this DFS method, because we are eliminating all the cases and we are also calling the recursive function based on the height difference. So after these four entries run, we should have both of our Pacific reachable and Atlantic reachable matrices filled out, and now it's just a matter of finding the common elements between them. So first of all, let's create a list of lists to store our result, and we'll just name it as result. Just going to iterate over the entire array row and column wise. and we are only going to check that if both the values are true in both the Atlantic and Pacific Ocean cells. So if both are true, we can add it to our list. So after this loop runs, we simply need to return whatever the result we found, and that should be our solution. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution also works. It is accepted by LeetCode, but the thing is it's not the most efficient solution. So let's see that if we can do some modifications. And one modification I can think of is rather than calling this DFS system right here and checking this condition all the time, what if we revert the condition, and if this condition is satisfied, we can just return it, and we can just continue before. So that's why loop breaks more times before. And if all of these conditions are not true, then only we will call our DFS function. Let's try to run the code. Okay, the code is working. Let's try to submit the code. Okay, we see some improvement in our code, and now it's a little bit faster than what our previous result was. So I'll be posting this code in the solution. You can check it out from there, from the comments, and let me know if how do you like the video. Thank you.